I first met David in 1989. We both started at the same year at Harvard Business School. I think the first time was when he and I went through this How to Teach course, which was a requirement. And I remember, you know, David, this bubbling personality who was kind of the life of the class. And that's part of his legacy. A big part of his legacy, as we heard it in the memorial service in September, is his family. But most of us have chosen to be academics in this room. And as academics, it's a curious life that we lead, because in addition to our family and the memories that we have as individuals, the legacy that we leave is our ideas, which are either embedded in our students or the people who read our papers or the people who talk to the people who read our papers. And so I think it's appropriate tonight that, of course, we should recognize David as an individual. But tonight's a night to talk about ideas, because I can assure you that ideas were always central to his life and to most of our lives as academics. So I'm going to turn it over to my colleagues to talk about the evening, and we're going to have 3 different parts of different sets of ideas. But very much, you know, one of the luxuries, and I'll speak to the academics in there, one of the luxuries of our lives is that we can live on for a long, long time. If you think about the people who have written hundreds and hundreds of years ago, and their ideas are still being discussed today. And that's an amazing gift when we can actually have something to say that goes from generation to generation. And I do think that some of David's works will in fact pass that mark, that we'll be talking about his work for a long time to come. But for tonight, we're going to talk about his work in different contexts. I'd like to hand it over to my colleague, Steve New, who will formally introduce the evening. Thank you very much.
Thank you very much, Peter. Thank you. Hello, everybody, and welcome to this evening's distinguished lecture. We're going to have 3 distinguished lectures. Shortly, I'll be introducing my colleague Matthias Holweg, who'll be talking about 3D printing. Professor Sir Mike Gregory, one of Dave's mentors from his Cambridge days, will talk about the idea of bringing manufacturing back to the UK. And Gary Pisano, one of David's long-standing colleagues and co-authors from the Harvard Business School, will conclude the input part of the evening, talking about the impact of machine learning. But before we do that, I'm going to steal a few moments to talk about David. I've had easier gigs, I'll be honest with you. But it would be good to review some of David's work and try to put it in context. And maybe I'll succeed in laying out a few threads which some of the other speakers might be able to pick up as we go. A few years ago, David and I were discussing how you could talk about operations management and still look cool. And we struggle with this. We both have a very large collection of unflattering photographs, and both of us have struggled over the years a little bit with our weight, to be honest. In fact, one year, 2011, I think it was, we had a competition for the MBA class to complete the sentence, "The future of operations management is." And the winning entry was, looking at Dave and Steve, not lean, which I thought was sad. And but Dave and I, we often joked about the stock photos, and he said he could never get the look he was really striving for. And then one day he did email me a picture which he said, "This is the closest I've got to nailing it." And that was a picture from 1976, and it was 20 years later when I first met Dave, but I always thought he was pretty cool. Now, some background information. Many of you know this stuff anyway, but Dave studied engineering at King's College in Cambridge University and did his doctorate on the application of artificial intelligence to computer-integrated manufacturing at Purdue University in the States. He was a chartered mechanical engineer, a registered European professional engineer. He had a postgraduate qualification in accounting and finance. He won the British Robot Association Research Prize, the Magoon Award for Excellence in Teaching at Purdue, the Apgar Award at Harvard, and later shared the Shingo Prize, which is in our field is a very big deal. Early in his career, he worked in engineering and sales and production at Tube Investments. At one point, he ran a consulting business developing microcomputer network operating systems, and he served on the boards of several companies, including Tech Data, a Fortune 500 company, for many years. And there's actually not many people who work in business schools who also serve at that level professionally. He was a consultant and trainer for many organizations, and he had long-standing connections to some of the world's greatest companies, GE, Wells Fargo, Novartis, IBM, many others. And there's lots of things we could say about David. I canvassed quite a few of his co-authors for comments and suggestions before this evening, and Bo-Won Kim, who's teaching in Korea, was at Harvard, wanted to emphasize his energy and his capacity to inspire. And Rob Huckman, another colleague at Harvard, wrote about his wit and positivity. And I could talk about his personal kindness too. They'd all be sensible things to talk about, but we're going to focus now on Dave's contributions to the field of operations management. And I'll begin with a summary. Dave's work has been incredibly influential. He said very important things, and he enlightened many students and companies and had a great force for good in the world. But he was influential, but not influential enough. The things he discovered still need to be said. And there's too many places where we still are in a very big need of Dave's wisdom and insight. And so for those of us left behind, we've still got lots of work to do, and I hope some of those thoughts will come out as we go forward. I'm going to mention 4 strands of Dave's work: computer integrated manufacturing, flexibility, strategic improvement, and then IT and cybersecurity. And I can't do any of them any justice. So we'll just start off thinking about computer integrated manufacturing. Dave's early work, largely coming out of his doctorate, was very squarely in the field of engineering. And I've got to be honest, I hadn't read these papers until I was preparing for this evening. But now, having read them, I can endorse them for their depth and their ingenuity. And mostly about this great excitement of applying technology to changing how we do manufacturing. And some of them are very interesting indeed. This one here, Architectures and Auctions in Manufacturing, is a very early preview of the technology which now we would call distributed autonomous artificial intelligence. And it's a precursor, although it's talking about different parts of manufacturing, it's a precursor to the things that now you get in Amazon and Alibaba warehouses when you have the little autonomous robots moving all the stuff around who are negotiating with each other and having little running auctions to see who's got the best, the biggest priority to follow a particular path through a warehouse. So it's very, I mean, that was very theoretical work, but work which then came to fruition 15 years later. Dave didn't invent that idea, but he did contribute to the as a throw of the progress of that stream of work. Andy McAfee, who many of you will know, wrote to me and said this about Dave's engagement with technology. Andy says, Dave Upton saw earlier and more clearly than just about any other academic that networked computers were the most powerful tools we've invented since the steam engine. I remember his excitement on seeing Java for the first time in the mid-1990s, and his certainty was that the great game of business was about to be played by different rules. Rob Austin, another colleague, wrote, I remember happening upon Dave in the very refined environs of Morgan Hall, in scruffy jeans and a T-shirt. He'd stopped into the office for something, but he'd spent the morning pulling coax cables around the ISP that doubled as his home. Those of us who've ever visited the Upton home in Boston will testify to that. Dave was the kind of guy you might just find as likely laying on a floor under a desk in jeans and a T-shirt with a screwdriver as in a lecture hall wearing a suit, talking to PowerPoint slides. He knew his subject from top to bottom. He was equally capable with a theory or with a soldering iron. And Dave really did know the technical details. You know, he invested an enormous amount of effort in really understanding the technology. And he understood things deeply. He understood how computers work. He understood how factories work. He understood how boardrooms work. And because he could understand at that level, he could make a great contribution to research and to teaching. And even though this highly work is very technical, you can see a bit of a thread of of what's to come. In this one about cutting tool management, which is I'm sure your favourite subject, there's a line in there which says, well, after a lot of very detailed technical exposition, the maths takes us so far, but in practice, all the real problems here are human problems. It's really all about the management of the people. Now, after that period, and largely involving this transition from Purdue eventually to Harvard, what Dave concentrated on was empirical research. And indeed, Brad Statz actually describes him as one of the creators of the whole field of empirical operations research. And for several years, the focus of his thinking was about the idea of flexibility. And here he was driven by a huge study looking at 61 paper mills in the United States, where he studied each plant in detail. And Brad comments that at the end of that study, he knew more about those paper factories than anybody else in the world, and I would add, probably including all the people who worked there as well. Dave's work here produced a string of very influential papers which have been cited thousands of times. Dave drew quite heavily on prior work by Nigel Slack, who some of us know, formerly of this parish. And Nigel's later papers acknowledged the contribution that Dave's work had made to the field. Now, the geniuses of Dave's work here is that he squares up to the fact that when he started writing this stuff, there was already a very substantial literature on flexibility. And there were lots and lots of different taxonomies. But Dave understood that they were all misleading and mostly, in fact, nonsense. And what was going on at the time was firms were investing very, very heavily in things called flexible manufacturing systems. And many of those applications and investments weren't working. And so Dave was trying to understand how this worked. People were not really understanding what they were talking about because they were thinking of things in not a very precise way. So Dave has a model of flexibility which begins with the idea that you can be flexible in lots and lots of different ways. And the word itself isn't very helpful because it covers so much. So, for example, imagine you're running a restaurant. So you can be flexible in running a restaurant by having a very long menu. Or perhaps you could have a very short menu, but change the menu every day. Or maybe you could have food which the customer can personalize. Or maybe you'll be a restaurant prepared to cook food to order at the customer's suggestion. Or maybe you could be flexible because sometimes you shut the whole restaurant down and use it for a wedding. Or maybe you could be flexible by opening at unlikely times of day, or being able to cook the same meal using different equipment or with different ingredients. There's all sorts of different sorts of flexibility. So what Dave says is this. I should just say that Dave's definition of flexibility has so entered the literature now that people quote this as if it's a dictionary definition. And often without citing Dave, but other spurious people who've picked up the phrase on the way. But Dave's model says, first off, work out what type of flexibility you're thinking about. And then think about what time scale you're thinking about. And then decide whether, on the whatever type of flexibility you're thinking about, whether you're talking about a range on a spectrum of flexibility, and that's what you're trying to achieve, or maybe you're wanting the opportunity to switch from a point to a different point on the spectrum between discrete locations, what he called mobility. And then, if you are going to do that, he says you need to say, what are you going to hold constant when you make that change? So, for example, are you going to try and have a change between one product and another, but keep the profitability or the cost level exactly the same, or the service level the same? So it turns out Dave's insight, which once you've thought it through, you realise cuts through so many of the previous papers on this subject and explains it with great clarity. It is so valuable. And it's valuable because it's grounded in the experience of what companies actually do and understanding that the generic, easy labels that academics like to throw around just don't match up to the So in Dave's work, particularly with the paper mills, he discovered some very interesting things. One thing he discovered was a very strong human element to how you manage flexibility in manufacturing. One of the things he noticed that a strong determinant of the flexibility of the plant was what the operators believed the managers felt was important. But that wasn't necessarily the same thing as what the managers said was important. It was what the operators thought the managers really meant. And some of the inflexible plants in Dave's study turned out to be inflexible for no other reason than a self-fulfilling prophecy. They'd been thought to be unflexible for some reason in the past, and so had never been given the product range which would allow them to exercise flexibility or variety in their activities. And counterintuitively, Dave also found no positive relationship between all the IT that was being expended to make situations, to make factories flexible and actual flexibility. In fact, what Dave discovered was that the clever IT that was being included in factories to facilitate flexibility generally made firms less flexible and led to a much higher likelihood of catastrophic failure. And so that, without Dave's clarity of thought, firms can easily plunge into new technologies with very muddled purposes. And if the people on the ground aren't looking in the same direction as the people at the top, or the engineers, or the IT people, then you can have disaster. Now, Dave's approach to his research work here on flexibility was driven by three key features. The first is that the research work was based on the lived experience of real organizations where the operations are observed at close quarters for substantial lengths of time. So Dave wasn't an enthusiast for sending off shallow surveys to lots of firms. He wanted to go and really understand how it worked in detail. He collected quantitative and qualitative data, and the quantitative data, I think this is a really important point, was analysed only to the point that the analysis of the quantitative data was commensurate with a meaningful question. So he wasn't collecting statistics and going fishing for some correlation or to try and construct a model for the sake of it. He had a meaningful question he wanted to answer, and that's how he deployed the quantitative stuff. Now, the other feature, I think, of Dave's work here is that his primary audience was always the practitioner. Dave wasn't interested at all in doing work that was only of academic value, even when he was publishing in hardcore journals. Dave's work always faced the issues raised by organisations and managers and workers. Brad Statz, again, describes Dave's ability to wade into the messy context driven by his immense curiosity. And as Rob Austin writes, he had a genius for finding the right question. And that approach of going and seeing rather than speculating fed into the other strands of Dave's work. So Dave did a great body of work on what I've loosely called strategic improvement, the idea of how firms get better at what they do. And he did major studies looking, for example, at Korean shipbuilding and Indian software development, always retaining a keen empirical focus. He was genuinely interested in what firms did and wanted to understand it and explain it. With Bo-won Kim, he worked out, for example, looking in Korea, that two shipbuilding firms that were otherwise very similar had completely different approaches to doing process improvement. One dealt with the workers doing incremental, on-the-job process improvement, and the other dealt with offline technical experts doing the process improvement. And what Dave and Bo-won Kim discovered was that this pattern of behaviour was the outcome of a very complicated story and journey for each of these firms. And it would have been impossible and probably ridiculous and dysfunctional for one of the firms to try to copy the other firm. So the idea of having a best practice that we can just dollop on an organisation doesn't work unless you understand the story and the context and the trajectory. Best practice always needs to be understood in terms of the rich context. And for IT and cybersecurity, which Dave moved on to do latterly, he followed the same model of detailed empirical work, trying to understand how people actually behave rather than naive or idealised model of how you'd rather hope they'd behave. Huge cybersecurity policies are pointless if no one actually follows them. Huge IT systems are completely dysfunctional if they just act like liquid concrete pouring over your business processes, insulating you from ever learning or changing again. So Dave really grasped that the way organisations' hubris And managers' laziness, intellectual laziness, got in the way of making effective use of IT and of exercising effective cybersecurity. Before you look at the technology, Dave would say, you need to look realistically at the strategy of the organization and the people you've got and the processes they're operating with. The leader's job becomes focusing the manager's collective attention. You want diversity of opinion, for sure, but you want everybody looking in the same direction. So, pulling out some thoughts from the different strands of Dave's work, I found a few things here that maybe we could return to. I didn't really expect to find this, but what you find when you read Dave's work on Block is you find it's all about people. And it's all about the fact that organizations need to develop capabilities and that technology needs to work again with the grain of the strategy of the organization. Now, Dave's research, massively influential as it was, still needs to be a live project. When we consider all the stuff going on now about the digitisation of manufacturing, Industry 4.0, industrial strategy, we need to understand how easy it is for organisations to get things wrong, how tempting it is to pick up a technical fix from one domain and plonk it down somewhere where it won't work. Dave did, though, once tell me that there was one context where it was very important that people didn't look in the same direction. One situation where it's very important that everybody should look in different directions. And that's because if you all stare straight ahead at the camera, the picture of your band is just not going to look cool. Thank you very much. Thank you.
Great, thanks. It's a pleasure to be here and say a few words. In fact, I did my doctoral work in the late 1990s on looking how car factories could actually make the cars that we actually ordered, rather than making lots of them to forecast and put them into inventory. And that directly built on Dave's work on manufacturing flexibility. And as Steve said, questions still to be worked on. Brad Statz and I are continuing the project that we started on sustaining lean improvements. The one thing where Dave and I didn't sort of really see eye to eye, though, was his love for IT, which I always thought was a bit of a necessary evil. Probably because I was involved in putting SAP into Siemens at the time and saw how much of an effort that was for what I saw was little payoff. That really changed, actually, when this became a reality. Now, what you see here behind me is of course, a 3D printing process. I call it the Terminator process, because what you're doing is you're pulling solid parts out of a liquid. It's a really cool process. You'll see it in a minute. And I've got a part for you here to touch. It produces fantastic surfaces. It's called Stereolithography. In fact, the idea is remarkably simple. But really, it's sort of one of the many new technologies that we see out here. The idea, by the way, if you're interested, is the liquid is monomers, sort of small molecules of plastic. And underneath, what you don't see here at the bottom, actually sits a laser that selectively hits the liquid. And where it hits the liquid, it entices the molecules to bond together. The more molecules bond together, the longer the chain gets, and until it eventually solidifies, and you get a part that you can pull out of a liquid. So, one of the many new ways, what we now call 3D printing, which of course is a class of many different ways of how we produce parts. I've got a couple of other examples here and tell you more about the strange shapes that we're looking at here. Industrially, we're probably looking, I'll pass this around here, we're looking at powder-based technology. So this is made in nylon. If you touch the surface, you'll still feel the powder. And you can print any powder. And this is made from steel powder, so it could be metal, it could be plastic. Careful, the edges are a bit sharp. But these are essentially, a couple of the many examples of new technologies that form this class of additive manufacturing, which really is sort of the perfect fusion of IT and manufacturing. Because the very file that is used to make these does not just merge the design, but also the manufacturing instruction. So what I could attach to a simple email and email infinitely around the globe is the entire design and the manufacturing instruction in a single file And you could simply make this at any point in time, at any place around the globe. Again, and of course, that is sort of, offers many new possibilities that we've seen. A couple of examples are on here. At the top, this is a company called Feets. It's a startup. You take 3 photos of your foot, and those photos, taken on your iPhone or Android, I guess, and sent over are enough to measure your foot, and the shoe will be printed exactly to your specification for $160, which, quite frankly, many of us will expend for a pair of shoes, but ones that perfectly fit. Of course, then we have got the medical applications, the hearing aid industry for the inlets. This is pretty much all 3D printed by now. This industry switched over in less than 2 years from traditional to 3D printing. Prosthetics, you see here, in fact, some very, very simple low-cost options available for emerging markets. You can print 3D print houses or emergency shelters, for example. And if you go down towards Headington to the medical campus, these are retina cells being printed. So just imagine, babies born in 10, 20 years' time will, withdraw stem cells from their umbilical cord. And then as they grow old, we can basically print whatever organs may be required in their lifetime. So those are the possibilities that open up. Maybe in the infancy, but some of those are of course, already well reality. This is printing of circuit boards. And of course, up here is a friendly command of the International Space Station, the first human tool not printed on planet Earth. Right? This is the wrench. It is functional, printed in one go. And of course, I had to print my own version, so you're most welcome to play with it. But that's basically what we are seeing. So you can see, it's heaven for an engineer, unless, of course, you have the great misfortune of working in a business school, in which case just making it work isn't good enough. But you also have to work out, can we actually make this, put this to good work and earn some money from it? And this is where this part comes in. All the other things you see here are generally one-offs, bespoke parts. This sort of rather cumbersome part here is the first volume manufactured standard part. The first part that, like 99% of all other parts we produce, is a standard and produced in large volumes. It's a fuel nozzle, and if you board in future an A320 Neo, the new engine option, or a 737 MAX, the latest generation, they will have new engines. And each of those new engines, called a LEAP engine, will have 20 of those fuel nozzles that are built into the engine. The first certified 3D printed part in aviation. That's why pretty much at every 3D printing conference, people will bore you with that story, and I, of course, have to do the same. For the simple reason that, of course, that is the real question, right? If 3D printing is to really change, or do a wholesale change to the manufacturing sector, will it be able to also produce standard parts in large volumes? Now, to answer that, I teamed up with an economist in an engineering school, talking about a fish out of water, Martin Baumers at Nottingham, where they have the industrial kit to play with, the real industrial scale machines. And we basically said, well, if you want to understand whether 3D printing is really going to change the way we manufacture pretty much everything around the planet, we have to understand the cost. And if you look at sort of a typical cost curve, so this is the unit cost and this is the quantity, and you look at traditional tool-based manufacturing, so injection molding, high-pressure die casting, pretty much any part that you see out there will be used by having an expensive tool and a very cheap variable cost of making a unit. So you have to spend a lot of money on the fixed cost for the tool, the cast, so the mold to make the cast, but the actual process of making then becomes very, very cheap. So what you get is a huge decay curve. The more you make, the cheaper it gets very, very quickly until it bottoms out. Now, if you look at the literature on 3D printing, basically the argument is that it's a flat line. Because, you make it once, you make it twice, makes no difference, it will cost you the same. And we thought, that's kind of strange, because really if you look at it, and this is where these strange parts come in, you could fill up a 3D printer with pretty much a lot of those. Or in this particular case, we've used an EOS P100, so the same 3D printer you'd find in most commercial operators. You actually can fit 55 of these parts into the build room. And you have fixed cost of setting up the machine. The technician has to set it all up. It has to be heated up. Then you have to print it. Then you have to process it afterwards. So in other words, you have sort of a batch element to this, which in our view clearly must have had an effect on the cost curve. So we enlisted the heroic services of our technician called Joe at Nottingham, who by the end of it would still talk to us, but clearly wasn't very happy because the experiments we ran was to make one, to make two, to make three, and each one, and you can see how this number would go on, and each time measure the entire process in terms of how much time he took, print it. And if you do that, you actually get to a cost curve that much more resembles this. What you see here is that you do have high fixed cost of setting up the machine, and very much like tool-based manufacturing, this also comes down as you utilize the machine better. So there clearly is an economy of scale argument, even in a process that we often say is free of economies of scale. We think that's not true. Now, this spiky pattern you do get because once you fill one build layer, it's well utilized. The minute you have one extra part, you have to open up a new slice. If you go back here, and in this one new slice, you only have a single part, and therefore it becomes less efficient. And as you fill up the full slice, basically the cost curve comes down until you open up a new slice. So eventually you'll see there are 11 little bumps in this chart. That's all nice and well, we thought. So we've shown something. However, what most studies in literature forget is that the assumption that in 3D printing all goes well is actually quite a grand assumption, because failure rates are really high. I print a lot, and I've got a couple of things here for you to play with. So this is something that we made in-house. Just to give you an idea, how delicate the prints can be and why there's high failure rates. So this is sort of a commercially printed one. But you can basically print very complicated parts, and therefore you also get failure rates. Here's another example. It's a fully functional part printed in one go. So it comes out of the printer as this, and you can turn the wheel. This is Nottingham's demonstrated part. And my favorite part, which of course I'll also show you, please be a bit careful with this, is a fully suspended vehicle, again, printed in one go. Now, as you can see, the complex geometry of the parts will mean that the more complicated the part is, generally also the failure rate in the print goes up. And if you consider the rate of print failure in here, the cost curve actually, the realistic cost curve looks more like this. Now, not so interesting if it weren't for the fact that the lowest cost actually occurs well below full utilization. And that again is very counterintuitive, because in traditional manufacturing, you would always seek to run the machine to the full capacity in order to get to the lowest cost. So I don't want to bore you more with cost curves, but just to show you what really stands behind all these sort of statements out in the press and in the academic writing about how this is going to change the world. Well, we think, yes, it's got great potential, but we need to understand the real nitty-gritty of what actually stands behind here to be able to infer how it's going to change the world of manufacturing. So just to summarize, fundamental different economics are at play here. It's agnostic to variety. You can print whatever you like in whatever combination you like. And of course, it's great because you don't have to deal with the expensive tooling that we have in traditional manufacturing, which now means we can cheaply print prosthetics, or you can have, this is Adidas Future Labs, have the sole of your running shoe printed to the exact specification at very little cost penalty. But it's not the case that making one has the same cost of making two, because fundamentally it is a batch process, it has setup costs, so it behaves in many ways very similarly to what we see in traditional manufacturing. What you also should consider is that lowest cost operation may well be below full utilization. So if you have an aircraft on the ground in Singapore with a broken fuel nozzle, you should think very carefully whether you want to print a single fuel nozzle at a lower probability of failure, or whether you want to load up your 3D printer to the brim and make it at a lower cost. And that's a trade-off, of course, that has the quality time element at the very heart. But that's what we need to understand to really make use of this technology. So let me just sort of leave with you sort of the 5 mechanisms which I think will, or how this technology will change the way or the world of manufacturing. Firstly, to make something we couldn't make before. These are the arguments of these sort of huge sort of improvements in geometry, freeform, right? The reason why the LEAP fuel nozzle here works so well is because this used to be made from 21 individual parts. And now it's basically printed in a single part with much better fuel flow and much less weight. So, clearly it's something that we couldn't make before. And it's not cheaper to print it than to make it in the traditional way. Secondly is this argument about customization. This is where the hearing aids, the dental implants, the prosthetics come, right? Make something unique to each customer, or the running shoes, right? I was told I was a heavy runner last time I went to buy trainers, which upset me a bit, but probably true, to fit into the ops group. But it probably means that I need more, fortifications in my running shoe. But clearly making something unique at little extra cost. Make it without tooling, which of course is the traditional argument that those of us who've been around for a bit longer will recall as rapid prototyping, the ability to just make a single part without having to buy or make expensive tooling. Make it just in time. So this is the idea that when you have, for example, a broken part, you would print a spare part on the spot rather than having a huge warehouse full of spare parts. In fact, we had a project at Kuhne, Logistics University at the time, where we paired up a 3D scanner with a 3D printer with the idea of putting that onto the service van to say, well, if a plastic part breaks, you'd put it on a scanner, scan it, and then print it. Now, to cut a long story short, the parts we tried to scan and print became bigger and bigger and simpler and simpler and simpler until eventually we gave up because the scanning technology is not yet good enough. But in future, you could clearly sort of think about making spare parts just in time. In particular, when you are, on a space station or, flying to Mars, this may be a good thing. Equally, make it locally. And Mike's going to talk about, why governments are getting interested in 3D printing in terms of bringing manufacturing back to the UK. But there are many aspects of this making locally that works. We've just finished a project here, in fact, with Alicia, a doctoral student, where we showed that you could take locally collected waste plastic and turn it into feedstock for a 3D printer. Now, plastics, of course, is a very contentious issue. So far, we've produced about 8 billion tons of plastic since the 60s, 70s, when it became a popular material. Less than 10% has been recycled. Just over 10% has been incinerated as part of household waste. And of course, the real problem is that the remaining 80% have ended up in landfill, and not just that, the landfill and our oceans. So we need to really think creatively how we could use technologies to take the waste plastic and make something useful from it again before it ends up in landfill and our oceans. So just to conclude, digital technologies, there's a huge hype around those, and Gary's going to talk about artificial intelligence. Same as 3D printing. Great promise, we don't dispute that. The point, however, I wanted to get across here is that we really should understand the economics of it first, and then qualify what actually we are seeing, and therefore, based on that, infer how it's going to change the world. Because the wholesale change, the revolution through total substitution, clearly will not happen, as 99% of all manufactured parts are standard parts produced in high volume. So really what we should expect is a gradual evolution where 3D printing technologies will come into our factories and take over specific parts, and probably more and more take over parts of various operations as the technology matures and as more materials become available and the general price per unit will drop. So expect, evolution rather than revolution. All right, thanks.
I'm delighted to be here, special occasion, and I feel very honoured to be asked to speak. I'm very sad because Dave's not here. And I'm very nervous because many people in this room could answer this exam question much better than I can. David, of all people, would have done it splendidly. He knew about the technology, to echo what Steve said. I can remember him coming from his pre-university year, having been in factories. He knew how to make things. And he personally installed the first BBC micro network in our labs. He knew how factories worked. You saw on there a glimpse of the paper he wrote on how to visit a factory and learn from it. And of course, he knew about strategy. Many companies were improved by his knowledge of the big picture. So I'm sorry to be second or probably fifth best at answering the question, but I'm here and it's too late to run away. So I'd like to start by telling you the answer, because some of you have come a long way and you might like to have a little doze. So I'll start by telling you the answer. Where did it go? If we think it's gone, why did it go away? A little bit of history we ought to think about. And then somebody famously said, you know, if you keep doing the same thing in the same circumstances, you're probably going to get the same answer. So we better think about what's changed, or are we going to continue in what for a while was a very unhappy state. So let's get a bit more upbeat and say, what are the opportunities? What might we do? And then how can we grab those opportunities? And in the words of the Pythons, of course, what can digitalization do for us? So first of all, I want to encourage you to take a broader view of manufacturing. This is not a new observation, but I want to persuade you that manufacturing is not simply the physical making of parts, important as that remains, as you've seen, but it's that whole cycle, understanding markets, R&D, design, production, distribution, service, and increasingly sustainability. So that's the big picture. People say to me, and I've been advised by very erudite people who realise that erudite is not a kind of glue, and they say to me, you see, Mike, manufacturing is about hands, and our hand, because they've done Latin, I think, and hands are expensive. So obviously you do manufacturing in China or somewhere else or wherever it is, the next place. And then they've gone, you see, because game over. But I'd like to persuade you that actually the manufacturing is a bigger story. And it's not just about hand, it's about lots of other things. If we want to get stuff back, we better, and as a humble engineer, I hesitate to recognise this, but actually we'd better make things that people really want. Engineers make really amazing things. And then we say, look, isn't that amazing? That was really hard to do. What do you mean you don't want one? Outrageous. Buy it, why don't you? So we better start thinking about what people really want. Otherwise, we're just enjoying ourselves. And then we better understand these emerging technologies. And you've seen a great example of an emerging technology from Matthias this evening. And there are many more. It's not just enough to create a technology. We think we're so clever. I like to say to my distinguished scientific colleagues, you know, science is just lying around there. If you don't discover it, somebody else will. But engineers have to create things that never existed before. Now, that's really interesting. I have a few bruises. Usually the things they throw at me aren't sharp. But we need to understand the technologies, not just say, oh, we've discovered another phenomenon. And then I'd like to spend a little time on the importance of scaling up fast. We tend to have a great idea, and the examples of this are legion. Look, I've done it. Off to the pub, lads. We actually need to make a lot of them quickly and make the things that people want. So why did it go? And a deliberately rather black and white picture of a factory in the 1970s. I used to have a real job making machine tools. And if you wanted one of our machines and were very nice to us, you could have one in a year. But if we didn't like you much, I'm afraid it'd be 15 months. We didn't think it was a problem. Austin's and Morris's were turning out, their factories were full. They couldn't make enough. Alfred Herbert's, the famous machine tool company in Coventry, in the 1970s was still the biggest machine tool company in the world. What was the problem? So we were very confident, but we weren't terribly efficient. I can remember going around factories, gone now, so it doesn't matter who they are, but there were people asleep. Well, it's nice work if you can get it, but you couldn't call it efficient. And then there's oil, and we forget about this. We weren't all doing silly things. We weren't all asleep. But then we had the oil crisis, and the exchange rate. You know about exchange rates? Well, actually, our stuff became ridiculously expensive overseas. It led to a, I think it's a restructuring is the polite word, but we carved out a lot of good stuff as well as a lot of bad stuff. And there were old habits. There were old habits on the shop floor, and there were old habits in management, and they deserved each other. We'll perhaps talk about the politics of it in the bar afterwards. But my old boss used to say he spent most of his time dealing with the unions. And the unions spent most of their time fighting a different battle. I was talking to a very distinguished emeritus person, and we were chatting about this period of history. And he said, do you know, Mike, people really thought during this period in the 70s that there were people plotting in smoke-filled rooms to overthrow the government. He said, we were. So these things were going on. And then, most unfortunately, those terrible Japanese came along and made cars that worked all the time. How unreasonable is that? There are garages all around the country which make a decent living by mending cars, and then people go along and make ones that don't break down. Quite unfair. So that's the world we were in. We shouldn't keep doing those things. They were pretty daft. But what's changed around us? Globalization, of course, you know. We're now saying it's a bad thing. Well, actually, for some people, of course, it's turned out to be a bad thing. But in many ways, it's made us globally efficient in the way we use resources. People's expectations have changed. They want things that are much closer to the thing they want. And if they're well off, they want one that only they have got one off. So they want a Picasso or a Ferrari or whatever it is. But actually people want things that are affordable. And we shouldn't forget, it's not just about customization. You can buy clothes fantastically cheaply. You might want to ask how they came to be such, but the volumes and the scale enable us to do that. There are priorities. People have different priorities. They want to have bits of stuff, or do they want services? And there's this connectedness that's going on all around us. And that rather dodgy graphic is intended to show you that the architecture of manufacturing, the architecture of industry, has changed quite dramatically. Things can be researched in one place, designed in another, made in another, joined up in another, and serviced in yet another. So we are in a different world. So how do we take advantage of this? See, people say it's all over for stuff. Well, I don't think so. Have you been to China recently? It's enormous. And there's India. That's enormous too. And you know what? People want a lot of stuff. And I don't just mean motor cars. What about food? Quite a lot of people are keen on food. That's a manufactured product. Clothes, people quite like clothes. So please don't tell me that it's all over for stuff. This is stuff and nonsense, if you'll excuse me. There are opportunities to provide things to people, and provide things to people at prices they can afford. So people around the globe who would very much like to have the standard of living that we all enjoy. Markets are growing. The digitalisation, and that's what, in this flipping exam question I was set, we need to address. It's about connectedness and responsiveness. And we need to do things quickly. The picture on the right, you will recognise, if you had a really neat idea, it used to take you about 30 years before people caught up. Now it's about 3 years. You'd better be jolly quick exploiting that idea, or somebody else is going to eat your lunch. And there have been rather a lot of people eating our lunch. So those are the kind of opportunities that are out there if we choose to grab them. And I'm afraid we have to grab them. I use the word grab advisedly. We can't just sort of sit in the pub and hope people will come along and say, can I have whatever it is? They really aren't. And the reason we got big was by, well, let's forget the first bit, which was sailing around and stealing people's countries. I don't know if you know that. Who's the stand-up comedian says, we used to go around, turn up at somebody's country, they've been there for thousands of years, and we say, right, it's ours now. And they say, no, we've been here for ages. And we say, where's your flag? We haven't got a flag. We have. Ours now. And so that was called globalization in the old-fashioned way. Now, look, I'm not proud of that. I think that's extremely rude. And to be fair to us, we don't do it anymore. But that was an early form of globalization. And it did mean that we had, and this is all rather unfortunate, but we understood how to do global markets and exchange. I think it was opium and stuff we used to sell around the world and stop people making clothes so that we could make them in Manchester. Now, none of this is terribly edifying, but we don't do much of that anymore. The more serious point is that we do need to make the right products and services and grab at these opportunities, not just wait for them to come to us. We do need to connect research to industrial needs. Now, I'll say a little bit more about that in a minute, and I'd like to say a little bit more about industrial emergence as well. Industrial emergence, because I had one of those, I used to have an almost real job as a professor, where you have to get grants. Grants are very important. And sometimes you get a big chunky grant, and before you know it, your distinguished colleagues have run off with it and done the thing that really interested them. I'm sure none of you have had that experience. And I had one of these grants, and I thought, at the end of this, apart from my colleagues having a great time, I really need to have something to say. Is there some really big issue that we should be worrying about? And we came up after a few cups of coffee or whatever it was, with industrial emergence. What's the big story strategically about the UK? Full of ideas, but why haven't the industries emerged? So I'll say a little bit about industrial emergence. And then I'd like to talk about focusing on new industries. We could make horseshoes. They're a very important artisan product. There are all sorts of things we could make. I'm reminded of there's a big royal commission at the end of the 1800s about, this is probably not in very good taste, but there was a lot of horse poo around because they all had all these horses and carts and things. And it was a real problem in London, so much poo. And so how are we going to do it? People were starting to design machines to collect this stuff. Fortunately, somebody invented the motor car, and so it went away as a problem. So really, the machine for collecting stuff was no longer necessary. We shouldn't be making machines for collecting poo. We need to focus on the new industries. What's coming next? Let's not... I don't know if any of you play football or hockey, but I was taught, I was never very good at it, but I was taught you have to, if you want to pass the ball, you have to pass it to where the player's going to be, not where he is when you can see him, if you see what I mean. So we really need to think where the ball is going to be. Now, research. We always use the term research as if we kind of know what it is. I think I must have done some of it, but I was never quite sure. And I found this little picture rather helpful. I'm sorry it's rather busy. At the bottom are the real researchers. These are boffins. They often have long hair, jealous, okay, often orange trousers. They frequently only work at night. And as my old boss used to say, you can always tell an extrovert computer scientist because he looks at your shoes rather than his own. So these are boffins, and that's what most people think research is about. And that's those splendid people, and I didn't mean to be disrespectful to the scientists who understand phenomena and work out what they are. Very important. Best done at night, orange trousers, few beers, pub. That sort of boffin-esque, I don't think that's a real English word actually, sorry. That world of research, which is what people might characterise it at if they hadn't been there. In the middle level, the enabling technologies, there are people also doing research, and I'm defining research now as new knowledge. There are many kinds of new knowledge. So there are people developing the technologies that come from an understanding of the science. And then there are people who are worrying about how those technologies are applied in purposeful ways. And we've heard already how much that was in Dave's style. So this is almost as close as we're going to get to a graph. There is one later on. But so if you bear with me, and along the top, there's that value chain of manufacturing, as I would like to persuade you. And down the left-hand side, that you can hardly read, but it's the same picture that was on the last slide, you can see now we've got a bit of a grid going on here of the value chain of manufacturing and the types of research. And do you know what, as they say? You need different kinds of research to tackle different problems. Down at the bottom is plastic logic. I think the technical term is they squirt blobs of gloop onto some plastic so you can make a bendy screen. Now, I may not have the technical terms right there, but you get the idea. And that's research. It's very complicated. It's engineering research, but it's right down at the science level. They're dealing with very fundamental things going on. In the middle is GKN, and GKN, as I'm sure many of you know, was Guest Keenan Nettlefolds, recently had their 250th anniversary, still a hugely successful company. They make the drives that go to your front-wheel drive car, so that when you're driving along and you steer and you've got a front-engine car, of course the power has got to go to the front wheels, and they go through these special joints that enable the wheels to turn while the power is going to the wheel. And that's very important because there's not a big market for cars that only go straight on. But GKN are right at the heart of this kind of research, which is about developing technologies. Now, you think I'm going... No, I wouldn't dream of guessing what you think. But Rolls-Royce, of course, have wonderful technologies, but they're also making machines that are worth more than silver. Over 50% of their revenue now comes from services that they sell. So, having managed to grab a little bit of loot from this grant, from the jaws of my rapacious colleagues, I'm glad this is not being recorded. Didn't mean it, chap, sorry. We had a go. I said, well, look, I think emergence is really important, but I have no idea how we study it. Fortunately, and this is a story of my life, they're all smarter than me, and they came up with this idea of emergence maps. Now, I get in trouble for showing this because they think people think I only like this picture because it's got Beatles Abbey Road in the middle at the top there. You see just about, sorry, it's a bit small. Which, of course, is a really great album, but many of you weren't born when it was out. Anyway, the point is that if you track the emergence of a technology, CT scanners now really important. There's down at the bottom left is Mr. Röntgen and his X-rays. And I don't want to go through the whole saga, but by mapping the events which led to CT scanners being now very commonplace, you can see what happened and what the interfaces were. And it turns out that the people who were doing the fundamental research for body scanners were paid for by the royalties from the Beatles albums, that's EMI, but we don't have any body scanner companies in the UK. How could that possibly be? Well, more of that anon, but the issue is we need to understand emergence and how it works. It's not terribly linear. You can't say on day one, I know how I'm going to get to the end. It's a bit more complicated than that. So, stay with me here. On the left-hand side, there are all these great ideas, this great science, this understanding of physical phenomena. Then there's the technology. Then there's the application. Only right at the end do we finally get to the market. And unless we understand, have some sense of how these things track through, we're going to lose the potential that they might have provided for us. So that's about how we do research which links to recognizable parts of the industrial system. It's about how we track and understand how industries emerge from ideas. But then it's about scale-up. And Many of you will be familiar, and this is the graph, so concentrate here because there will be a test. On the left-hand side is money being spent on research. Great, I like it. Once you've written the paper, I'm off to the next one. There's another grant to be got. I can't live forever on that paper. And so neither can the research councils. They want to fund new things. And that green line, money for this new idea, gradually drops off, and the research councils say, well, it's industry's job now to pick it up. Industry is the blue line, and they say, well, if they know at all what's going on, they say, well, that's a half-baked idea, I can't do anything with that. Oh, forget it. Now, really where we want to, even when they get it and start, all sorts of things can go wrong. We've got one that works, but it looks horrible, so nobody wants to buy it. We haven't thought about how to make it. Oh, damn, it's a really great idea. You want to make it as well. Ridiculous. And so on. All sorts of reasons in these blue arrows why we don't go all the way through and why we lose the potential of the ideas that we're so famous for. And so I'd like to persuade you that scale-up is not just about making lots quickly, because that's easy to say. And much of the debate about scale-up today is about getting more money in. And of course, that's important. To scale up, you do need to have money to invest. But actually, there's a technical and organizational part of scale-up, which is that for different levels, you need different capabilities. And so the kind of value chain that you need varies. And so if you'll bear with me with my putting together my grid and my graph, this is getting super technical now, you can see that we need different kinds of research as we go through that emergence process. And because regenerative medicine I've become increasingly interested in, I must say, for reasons which I'm sure are quite apparent, but it's an example of a new industry, something that's coming, something that we're going to have to do. It's not I love motor cars and I love old-fashioned bits of metal, but actually what people are going to buy is being regenerated. Be good, wouldn't it? I'm not going to point at individuals, but some of us, and I include myself in that, would like a little bit of regeneration. Not too much. I don't want to go too far back. That'd be awful. But regenerative medicine is an example of the kind of thing where there is going to be a huge market and where this big manufacturing story is critical, and where if we don't scale it up properly, we'll have lots of great scientific papers and no doubt a heap of Nobel Prizes, but we won't have an industry. And so here's the example of regenerative medicine. There's the science, there's the paper down on the left. Now we think perhaps we can make engineered structures somehow. That's a bit of engineering. And then we've got to make it. Now that could be extremely tricky. Takes a long time. It may be that the method we used to make the first one won't do for 10, and the method that does for 10 won't do for 100, and so on. So we need a much better understanding of the nature of the production processes at different scales. And then we need to get it out to people. People say, I've got some great stuff in my factory, come and get it. Well, they won't. There's a famous story about a new product of artificial skin. Built the factory, fantastic, forgot that it could only be transported in cooled containers. So if you haven't got a cool delivery system, cool not in the earlier sense, but cool as in not very hot, then it's no good. You can't distribute the stuff. Now, of course, everybody knows that if you want to get anything anywhere on the planet, you put it on the Coca-Cola lorry. But more seriously, these issues of logistics and distribution need to be considered right at the beginning, not at the science level, but certainly as soon as you start thinking about engineering, and certainly when you're thinking about manufacturing and automation. So what can digitalization do for us? I'm never sure whether it's digitalization, which looks a bit too much like digitalis, which is dangerous stuff, or is it digitization? But let's not get into that. What it can do is enable advanced production technologies. And Matthias has given a great example of a production technology which is totally dependent on digital technologies, and there are more. It can coordinate production, supply and distribution, and I hope I've persuaded you that it's that whole system that we need to get right, not just the individual bits of it. Also, it can help us accelerate the scale-up, the research, the innovation, the scale-up, if they're all connected together, and we can refer back to what went on. Once upon a time, you wrote your paper, half the stuff in the PhD, probably 3/4 was thrown away. When the research student moved on, there's just a bit left, which is a thesis, which is only half or a quarter of the things that are actually discovered. But now, if we're clever, that knowledge which is generated should be accessible and rapidly accessible and join-upable. Another not very English word, I'm afraid. And then it's about, as we've heard already, where Dave excelled, was to integrate technology and operations and strategy. Technology, very important, needs to be there. Operations, better be lean. Strategy, we better have Porter and Teese. We need all of those things, and Gary, of course. But we need to be able to meld them together in some way. And if we could do that, then we would be able to exploit our huge global reach. Not saying how we got there. We do have global reach. We do have the English language. We are seen as kind of fair sort of players. We are astonishingly well liked around the world, despite, even in China, for goodness sake. Anyway, let's not open old wounds. The reality is we do have global reach and we have unique capabilities of science and research. So, sorry, it's a very long way. You could have just stopped after the first slide, but that is all really to give you some justification, I hope, for my answer, which is yes. And I must end with the way that Dave's legacy is very central to all of this. What did he do? He engaged the best minds. When he was a student, he was one of the brightest students. He taught the best people. He worked with the best companies, engaging the best minds in these kind of issues, which are not traditionally seen as things which are intellectually very demanding. They really are. He made a difference to real businesses. It wasn't just enough to write the paper. As we've heard, he wanted to go and make a difference. He was a citizen of everywhere. That's supposed to be not very fashionable. I think it's absolutely vital. Citizen of everywhere is a citizen of nowhere. What a load of rubbish. Dave could drop down anywhere on the planet and do good things and make a difference. We need to learn from that. And he was more than a strategist, an operations person, manager and technologist. I'd like to think of him as a pioneering industrial systems architect. That's what we're missing. We've got great engineers, strategists, management people. There are not enough of any of them, but what we're really short of is industrial systems architects, people who understand the whole system and know how to make it better. Thank you very much.
Mike, thank you very much indeed. And so now we are very honoured to have Professor Gary Pisano. Gary, over to you.
Thank you for having me. It's my honor to be here. I wish I were here for a different reason, but I want to start by commenting that, you know, in many ways, this is a really appropriate talk to give on this occasion because the topic, the impact of machine learning on organizational learning, was really at the intersection of what Dave's work was about. For the last 3 decades, I've done a lot of work on organizational learning. And my interest in organizational learning, as it plays out in operations, was stimulated by Dave. When Dave first came to the Harvard Business School in 1989, I was on the 2nd year of my faculty then. And that's really where I got interested in the whole issue of how organizations improve and how they learn. And Dave was really, he was a technologist. He was a pioneer in, as we heard, in machine learning. And yet, as we heard in the opening comments, he put people at the center of his work. So there's this really interesting confluence of the sort of what's happening today with technology in terms of improvements in machine learning and where we've been in terms of how organizations improve. And he was right at the center of that. And I dearly wish, as I've started to get interested in these ideas, I dearly wish he was around to collaborate with. It's also really appropriate. This is a set of issues. While I've spent a lot of my career thinking about how organizations improve, I'm much newer to trying to understand the role of machine learning in that. So this is an occasion where I'm presenting really a very preliminary sketch of my thoughts. It's more of a question than an answer. And yet again, throughout my career, I always trusted Dave with my very earliest ideas. I'd go down to his office and I had no fear of tossing out the earliest ideas, sometimes stupid ideas, and he was just wonderfully receptive, always incredibly helpful and thoughtful and encouraging. And so, in some sense, I feel here in his home that I can trust you as well. I'm going to lay out some very preliminary ideas, and again, more questions where we are in terms of this intersection of what's happening today with technology, improvements in machine learning, and what does it mean for how we've taught organizational learning, and in particular, all the things we teach about the role of people and culture in organizations and having to improve it, does in some sense the improvements we're seeing dramatically today make that paradigm obsolete, or what impact does it have on how organizations should try to improve in operations, and what should we be doing research on, and what should we be teaching differently? So it's just sort of three basic points here, and I realize we're late in the day, and it's always you're the last one on a long day for everyone. The risk of folks dozing off is high. It reminds me of a time I was teaching and somebody fell asleep while I was teaching, and I said to the student next to him, "Can you wake Joe up?" And the student said back to me, "Professor, you put him to sleep, you wake him up." I certainly hope that doesn't happen to me today. I'm going to start briefly by talking about organizational learning, what we know about, what's the model, and then talk a little bit about what I call the automation of learning. That's, everything we're seeing today around machine learning, artificial intelligence is nothing more than the next step in automation. And what we're doing is we're starting to automate learning, and then talk about the implications of this. So first, organizational learning. What is it? It is a process by which, in some sense, you can measure it. Organizations improve, their costs get lower, their yields get better, their quality gets better, they get more responsive. That's kind of the outward manifestation of it. What really happens, interestingly, internally, is a process by which organizations, I would say, they change what they do. There's a process change that is durable. So it's not they just happen to have done it differently today, they changed their process, and they improved, but then tomorrow they went back. So it's got to be some quasi-permanent change in their processes or their behaviors. Now, what we know from now, literally decades of research, 75 years of research on this, we know it matters. If you look at any of the data on productivity improvement, at a company level, at an industry level, or even at a national level, well, disruption gets the headline. About 75% of productivity improvement is kind of continuous incremental process improvement. So it matters a lot. Second fact is we know that improvement is highly correlated with experience. So again, we can go back to the early learning curve studies going back to the 1930s and continuing through today. I've done some of those studies, and you look at the effect of volume and cumulative experience on improvement, and it's there. So we know experience matters. It matters at the organizational level. It certainly matters at the individual level as well. But the third fact is potentially the most interesting one about what we've learned about organizational learning, which is that management really matters. It's a fairly complex phenomenon in the sense that if you look at the data, not every company improves at the same rate given the amount of volume that they have. So companies tend to be on different learning curves. So for the same amount of volume, I might, be at a certain place in terms of my performance, and you may be much further along. So somehow different organizations are better at converting the experience into actual improvement. And a lot of research we've done, and this is research I've been involved with, and Dave did a lot of this research as well, digging apart what's going on in the process of improvement, this complexity between how the learning takes place and who's involved and why, what's the route? Is it the worker training? Is it improvements in actually the equipment you're using? And how does that all play out? A big part of our understanding of this is you can kind of decompose a basic model of, this is really a basic model of learning. I think even individuals learn this way, but we can apply this to organizational learning following somewhat of, I'm going to put it up here as a somewhat linear process, more just to describe it. That is, it starts from data. Data is a broad word. Data can mean quantitative data, it can be qualitative data. It can be data that is easy to codify and digitize. It could be data that can't be digitized. So data comes in a lot of different forms. It can be generated by experience. That is, we're just doing stuff and that's experience. But we can also generate data through experiments. So I define an experiment as simply a contrived experience. So we get data. Data, in some sense, are facts. Nothing more than kind of raw facts, facts about an event, facts about a phenomenon. They always have to be backward-looking. They're not forward-looking. When we start to put structure around those facts in a way to give them meaning through comparison, sometimes through analytical tools or statistical methods, sometimes through simple processes of individual reflection. Again, it doesn't have to be quantitative. Historians all the time make sense of facts by doing qualitative analysis. That's where we have information. We can begin to kind of give it meaning. But knowledge is a process of actually interpreting what that information is. And that knowledge can be predictive, it can be diagnostic, it can be prescriptive. It very often has the nature of a kind of if-then statement. If I see this, then that. If the temperature of this process is above 50 degrees, then the yields will fall. If this particular part doesn't fit, then change that. So there's a lot of it's oversimplifying it a bit. But the learning, I want to emphasize, only takes place if the organization acts on it. So knowledge is not the same as in the context I'm describing organizational learning. So there has to be some change in change in behavior, but you could also say a process that is durable. And we have different ways to start to think about learning as building understanding. And I'm not going to go through this in detail. This is a framework put together by my former colleagues at Harvard, Roger Bone and the late J. Kumar, around the idea that part of what happens in organizations is, particularly in operations, the understanding of process can get deeper. You can measure learning by how much deeper you're going. So you can think about, at some level, a stage, a process, you have what they call complete ignorance. You don't know what is relevant to the outcome. Sort of think about pure art in some way. You might be able to judge whether you like something or not, but you have no idea why. That's a very hard process to replicate and to scale up. And as you gain insight, the whole learning cycle brings you down those stages. So you get awareness, you can start to measure things, control things, et cetera. And you ultimately could potentially get to a state where you have a kind of complete, detailed model of the process. You know all the variables, you know how they interact, and you know how to control them. So we can think about learning proceeding that way. Now, one thing that as we start to think, well, what is it? How do organizations actually do this? What do they do? This is research in the last, I'd say, 20 or 30 years, and a lot of it looking at companies like Toyota. A kind of, I'll call it the standard reference model has emerged, and it's generally the kind of Toyota production system, although there's variants of it. But so many scholars in operations have written about it, and so many practitioners to think about, okay, so if you want to explain why some organizations are good at this and why some are better at learning than others, it comes down to a few basic things. Again, sort of modeled along the lines of the Toyota production system. It's a set of tools and methods for problem solving. It's a set of principles and behaviors. So, for example, an organization that says, we only want no tolerance for defects. That's a principle. Or respond quickly to problems. That's a principle. But most importantly, what comes out of this work time and time again, I think this was echoed beautifully in the opening comments about Dave's work. It's really a kind of set of cultural norms and people. So that what we know is that in organizations where workers are really engaged in the process, where they're well trained, where they're not afraid to speak up, where, say, for example, in Toyota production line, they can stop a production process if there's defects. All of those things seem to contribute positively to the learning that occurs in the organization. At the end of the day, it seems to be that in the current model of organizational learning, it's an incredibly human-centric phenomenon. And it's not just about the tools. And I think a lot of practitioners would ascribe to that those who have tried to implement things like Lean Six Sigma or the Toyota production system or any other improvement effort, if you don't have the people on board from the shop floor up through the management level, it tends not to work. So that's kind of where we are. Now, in parallel to this, what's been going on, the sort of second stream, I want to talk about automation, which is widely talked about today in terms of the impact on jobs. That's not I think that's an important issue. That's not what I'm going to focus on now. Automation, first of all, automation is not recent. In my mind, I'm not an engineer. I'm just an economist. So, to my mind, my understanding, the way I look at it, automation, there's two properties of automation. So one is the substitution of what I'd call non-animal power for some kind of animal power. So if you mechanize things, you use the power, steam, electric, chemical energy to replace the work that was physically done by either a human or an animal, a horse or an ox. That's one piece. There's the power part of it. And then a control mechanism, something to provide a feedback mechanism to allow the system to regulate, to self-correct the behavior of the system. We've actually been, you can kind of, if you really want to push it, we've been going, the water clock was invented by a Greek engineer in 2012. So in some sense, that was an early form of automation because it used water to power the clock and it had a feedback mechanism. So it was a clock. The clock was a form of automation. The thermostat in the 1600s was invented in the Netherlands. The power loom was probably the first piece of industrial automation. We've gone through several what I call epics of automation. One was the application of, a lot of automation started with the Industrial Revolution was about the application of power. It really was substituting some non-animal source of energy, non-living source of energy for a living source. It was, steam, electric, chemical. It was really about horsepower. In fact, the term horsepower, I think, tells you a lot about what the focus was in that kind of automation. It was providing these alternative sources of energy in order to move objects you couldn't move before or move them more quickly. So it was really sort of epic one. Really starting with the Industrial Revolution was about the application of power. We then evolved, starting more in the 20th century, give or take, kind of the first part, the application of mechanical control. So being able to create literally physical mechanisms to create repeatability and speed. So you can think about first generation automated production. You'd set it up mechanically and then it would run and you could keep producing the same thing over and over again. When you finish producing that, you'd reset up the machine. But that was an application of mechanical control. The third epoch really starts about the time in the early 60s as we start to have digital technologies and computerized control, we get programmable logic. So that allowed us to have repeatability, precision, and speed, but most importantly, flexibility. And so we can now start to program equipment, change what it does simply by reprogramming it. And I should add that this form of automation we see in lots of places. So think about an ATM machine, a bank machine. I don't know, do you call them ATMs here? We call bankomat. They're called bankomats in other parts of Europe. ATM. That's programmable. Every time you go in there and you push what you're doing, you're programming to say, don't give me cash or take this deposit. Or think about autopilot on an airplane is a form of programmable logic. What the pilot's doing when they're changing the coordinates of the navigation, they're just basically reprogram the navigation system. Okay. And then, let's say in the last 20, 30 years, we've started the application of software tools for cognitive tasks. So things like computer-aided design and simulation and problem solving. They were tools to aid our problem solving. So substituting things we had to do with our mind, we can now they can enable us. They helped us to calculate. But none of these were really about learning. So none of these automated the actual task of learning. Autopilot didn't learn how to fly. Robots didn't learn how to produce better. You could discover new ways. We could discover new ways to make something better, and we could reprogram a computer. But it didn't do it itself. That's what I think has started to change with machine learning. So I would define machine learning as, well, sorry, I don't define it. The machine learning is defined as building computers that improve automatically through experiments. So if we go back to that experience cycle, the experience kind of information, knowledge, learning loop, that's what's going on with machine learning. It's taking data, it's converting it through a lot, and I'm not going to get into the different methods. There's different types of machine learning, different technical approaches, but then using that to generate insights about things that can be done better. I would define machine learning as really automating the learning process. And it's the first time we've begun to automate learning itself as opposed to automating the tasks, or in some different way to pose it, we're automating the task of learning. And in some way, what machine learning helps us do in some context is a tool to help us kind of move up or down, however you want to define it, up the stages of knowledge from 2 to 3 to 4. It helps us go deeper through the analysis of that data. Now, there's examples of machine learning today in manufacturing all over the place. Predictive maintenance is probably the most common one, where through analysis of the data on how a machine works and when it breaks, you could start to say, you know what, if the temperature of that machine goes above a certain a certain degree or certain level, or there's a certain amount of vibration, again, anything you can measure, it'll correlate it and say, you could have a problem. I mean, this has been done actually for quite a while. We see it with aircraft engines, probably the longest, elevators in a non-manufacturing setting. Energy maintenance. So Google had a project looking at how to reduce the amount of energy. Think about that in their data centers. Data centers are actually we don't think of them. They are big manufacturing plants. They consume a lot of energy, and figuring out how to cool them. Well, using algorithms, they could figure out when the heat was going to come, so you could regulate the amount of cooling as kind of predictively. Again, I'm not going to go into all the details. Root cause analysis, remote quality monitoring, and machine vision for quality control. These are all applications of machine learning for manufacturing, and many more. And it's dangerous because I say today, these things are evolving incredibly quickly. And so what is quote unquote possible today, it'll be very different in probably 2 weeks and a year and 5 years. So it raises, though, in my mind, as we begin to start to, and we're kind of still at the beginning of this whole process, but we're starting to automate learning, then it raises a really interesting question. What role is there, if any, for traditional organizational learning? So, like all that stuff we teach about quality and getting the workforce engaged and being good at problem solving, is that relevant anymore? In fact, if I posed it in really pretty stark terms for myself as a teacher, should I be teaching the Toyota production system anymore? Or should I just teach my students machine learning? Does culture matter? Do people matter? And can improvement be a source of advantage in the age of machine learning? So suddenly, does this start to level the playing field? So anybody who can get access to these algorithms, and by the way, these algorithms spread very quickly, or certainly you can hire Google to help you do this stuff, or Microsoft, they'll sell you this stuff. Then suddenly, is there any basis of competitive differentiation in my operations anymore if that's the name of the game? So I'm going to take a shot at kind of laying out my preliminary thoughts on this. First, I think context matters. I think when we start to talk about where machining is, I'm gaining an understanding of it. And again, I'm still pretty new at the game. You need a couple of things in machine learning. First, you need data. Volume of data matters, and that's typically correlated with the amount of production volume, and in many ways correlated with the amount of automation already in the process, because that's the instruments by which you can pick up the data. Not completely true, because you can just videotape a lot of what goes on, or right? You can video what's going on and use that as that becomes data that can be analyzed. So not necessarily completely linked to the amount of manufacturing. And some degree of process stability. That is, you need data that you accumulate over time that have, in some sense, some structure to it so that you can make sense of it. So if it's not comparable, if you suddenly change the process completely every 2 days, then in fact it's hard to accumulate enough data on any one set of events to be able to make predictions. And that's why today what you see is it's largely used in predictive maintenance. Or think about an aircraft engine. You're collecting data. The aircraft engine hasn't changed. It's just cranking out data, and you have data on when they break. But if the engines were changing dramatically all the time, then it would be hard to accumulate enough data. So there's some places where, in some sense, if you think about craft production, I was in a shoe factory in northern Italy. It was the Armani shoe factory, where they make shoes that are $600 or $700 a pair. They probably produce 1,000 pairs per model, per size, per model, maybe less. That's not a place where I think we're going to see a lot of machine learning. It's just its relevance is probably not very high. On the other hand, there's places where we're already doing it. If you think about some super highly automated production today, like semiconductor production, it's heavily instrumented already. I think we've already shifted out of the old paradigm of organizational learning in that setting. Most of the learning does not happen on the shop floor, and even the engineering itself is more kind of data science. I mean, in some sense, process engineers in that context are data scientists are becoming the process engineers, and the process parameters, relatively speaking, are somewhat stable. That could change. But that leaves this whole vast middle ground, which is probably 90% of manufacturing and service operations, where we have some automation, but we have a lot of human labor involved in the process, where there's some degree of process stability, but the processes can also change. How do we think about this link between what we're learning, what's happening with machine learning, and this world of organizational learning, and how do we put these together, and are they complements or substitutes? My general sense, my hypothesis here, and it's just a hypothesis, I'm going to take a stand and say I think they're complements. So I don't think machine learning, to answer the question I posed at the beginning of the talk, I don't think machine learning makes organizational learning passé in most contexts. I think, though, if we learned any lesson from studying, and again, Dave's work was spot on about this in thinking about flexible manufacturing, if we learned anything from that body of work, it's when new technologies come along, they change what the organization has to do. So it's not that machine learning is going to be plug and play into our existing organizations. The organizations that will do best with it are actually going to change the way they do organizational learning. They will adapt. So one model will adapt to the other. And so we can think about some of the changes that are needed. A couple of things to keep in mind. Again, it's dangerous to say what the limits are because the frontier is getting pushed quickly. First of all, to recognize there's some kinds of data that is collectible and that is not. Machine learning works for data that is collectible. There's a lot of data that could be very relevant that's not collectible. So, for example, how engaged is my worker on the shop floor? How engaged are they? How happy are they about serving a customer in a service setting? Right now, we don't really have good ways to pick that up, and we know that could matter a lot. So while we can instrument a lot of things to collect quantitative data, there's some things we may not be able to collect data on that could be extremely relevant. We also know there are prediction errors even today, and they're always going to be prediction errors. And so what you need is you need a workforce at all levels who are very good at judgment. That, if you think about what pilots do, really good pilots use judgment about when to follow the autopilot and when not to. And they also know autopilot does not work under all circumstances. There are exceptions. A couple of years ago, there was a movie was made out of it, so you probably know the story, the guy who landed the plane in the Hudson River. Autopilot is not going to help you at that point. The autopilot was not designed for 2 engines go out. Okay? So you need but there's less dramatic cases. And by the way, good physicians do this. Professionals do this. This is something we also need to be, as we think about in business schools, what we're training people. We're training around judgment. It's the exceptions. What are the exceptions? When do you listen? When don't you listen? And what it says, there's an interesting implication is that I want to explore, that I'm exploring further around workforce design. It means average is no longer valuable because average can actually be handled by most of the algorithms. It's the exceptions. It's like when the plane loses 2 engines, I shouldn't be using these examples, I'm flying tomorrow. When the plane loses 2 engines, an average pilot isn't good enough, okay? You actually need the superstar pilot. The same thing I think is becoming true in production settings. That when the systems aren't working, things are really a mess and you need really great people, not average folks on the shop floor. Third is process innovation, so changing. So we talk a lot about what happens with machine learning, and people always talk about how fast it learns new games. Last week, an algorithm was taught to play a new game within a few days. But games have structure. There's lots of problems that have no structure. And if you jump from kind of you kind of go completely outside your data range with enough process innovation. And we as humans are very good at learning from incredibly small samples. So think about how we learn language, or the analogy I like to use with young kids. If they touch a hot stove once, they generally figure out, don't touch it again. Okay? Computers actually have to have lots and lots of repetition to kind of get some of that stuff. So a key part of innovation is not just the incremental, but it's also the bigger changes. And we don't want to get stuck in a situation where we're kind of optimized into some small kind of local optimum. Yeah, that's right. See, if you had a machine learning algorithm, it would say, I'm in a meeting, it's going to shut it off. So, and then finally, where we are, and this is a little more controversial, or a little more, maybe this could change, is theorizing. That is actually a lot of what good improvement is about, is understanding not know how, but what is called know why. So understanding why things occur. It's not just a black box. Today, and again, I want to preface it, today, and somewhat in the near future from what I can understand from my colleagues in the computer science department who are 100 times smarter than me about this, is machine learning is not generating theories. It's helping us understand very powerful associations, but we don't know why. It's a black box, and that's dangerous. So we still need human problem solvers to understand why. We need it for another reason. What we know is that in both production and service settings, workers, just telling people follow the rules is generally a bad idea. They get very disengaged. For them, in organizations which do what they zero defect type cultures, it's not do this. You have to explain why you have to do that. You can't get people to buy into that. And if you can get people to buy into it, they will do it. If you just tell people to follow the rules, they tend not to want to follow the rules. And those are exactly not the kind of people you want in your operating setting anyway. So we need to be kind of shifting how we think about what improvement is. It's developing deeper theories. We don't normally associate that with what we're doing on the shop floor, but that's exactly the way it will change what's going on. People on the shop floor will become like our kind of production workers and our frontline service workers. They're really going to become more like data techs. So we hear the term data scientists. They're going to be not just they're not monitoring equipment. They're monitoring the data. They're going to need to understand the algorithms. They're going to have to be trained very differently. As I mentioned before, average is no longer valuable. Third, again, learning is putting things into action. Machine learning, unless you're in a fully automated production setting like semiconductors, it doesn't actually put the stuff into action for you. You have to do it and you have to choose what to do. And that's where fast experimentation is going to matter. So can you take an idea, a hypothesis generated from your machine learning algorithm, and try it? And how fast can you try it? That's a whole nother set of skills one needs to have in a production setting or a service setting. And so I guess at the bottom, at the end of the day, Dave's suspicion, Dave's view, Dave's work, that workforce engagement, training, culture, that they met is still important. They still matter a lot. It's just that the way we're going to do this stuff is probably going to be very different. And this is a topic where we're just scratching the surface. So I hope others will be jumping in this venture to help us understand this topic much better. Thank you.
Thank you to all our speakers. Three absolutely stunning talks, I think, and we're very grateful for your participation. And I think it's really resonant to me that all the things we talked about, as Gary's just been saying, really connect very strongly with Dave's work. But now I think our discussion should think perhaps about Dave, but also about the future and about some of the challenges that have been faced. We've got some important questions here. I'm hopeful that as William Fritz and Alexander Montag are in the room. So can I ask you guys to be the custodians of the mics? Because we're recording the event, we need to capture the questions as well. That's right. Yeah, you got it. You got it. Yeah. So I wonder if I might ask for questions from the floor.
What's the expertise of our two colleagues here?
These two colleagues here, they're good microphone handlers. They're here. Oh, sorry.
To ask questions or?
Yes, please, Alistair. Yes, we'll await your question.
Okay, sorry.
Well done.
What I was interested in is it's in connection with how Dave saw things. In London Business School in the late 80s, we used to take 40 executives from UK to Japan to see what they did. And they went round a number of places, hopefully to get the answer. Well, firstly, as you know, there aren't answers, but they were going to get the answer. So that rather distressed after a few visits, I said to one of them, "Are you getting what you want?" And he said, "I don't think so." I said, "What did you want to get?" And I said, "I wanted to see a 19-armed FANUC robot putting together a Camry in 10 minutes. And I said, "Then what would you do then?" He said, "Then I would get the number of the FANUC and buy one." But it's not on. And it was a lot to do with, you know, I said, "Look, if it was so, they'd never let you in." And therefore, they know some other things. They're inviting you in because they're proud of what they've got, and they're proud of everything they've got. Everything is about 70 things, not one robot. So that I'm interested in how the game of copying and the question of everything in a way is on trial, if we can live with it. Those two things. I think we have to copy. We have to copy. It's so much of a shortcut. But it was on trial for them before we pick up the copy and say it's on trial with us. And it's a nuisance that, because it would be nice if we had answers, but it is on trial. And in the organizational area, as indeed the technical area, everything's on trial. But we have to copy. And hence, education as a role.
Alistair, I'd like to translate your lecture to a question for Matthias and Mike.
It's the most offensive thing to do in a classroom is say, "Professor, is what you mean by this X, Y, Z?" Get out of it, Steve. Our friendship is over.
Very good. But I think that question of learning from others and copying practices is quite important. I'd be interested to hear from all the panel, perhaps maybe starting with you, Matthias, about in the domain of digital manufacturing, who should we be copying?
Well, actually, it's quite early on, right? So we haven't yet seen the Toyota of digital manufacturing. I think we've seen sort of different models emerge, and within each business model, like the contract manufacturers, the Shapeways, and others, we've seen sort of good and poor performance, a bit like what Gary described, how far along the learning curve they are. But yeah, I think we're still getting to grips with, the process stability, to use the language. To a level where really sort of the copying becomes a really interesting game. So far, I think we're very much on the sort of the first upward slope on the learning curve. So yeah, I guess you could go and copy from Shapeways and sort of learn about how to pack up, 3D printers in a good way, how to sort of organize around. But I'm sure there's a lot more yet to be learned to really become the Toyota of digital manufacturing.
Mike, what role does going and seeing and benchmarking and capturing what others are doing going to play in the revitalization of national economies?
Well, I think it's important to go and have a shufti and see what's going on. I think it's the level at which you take away the lesson. I think you quoted Dave as saying, best practice is a very dangerous word because it may be best in one context and not in another. It's like going into a big process plant and they've got all these dials and you look where the dials are and then you say, "I'll go back to my factory now and I'll set all the dials to that and everything will be fine." Well, of course it isn't, because what's behind is completely different. So I think it's about getting your observations about the practice down to a sufficiently granular level, and you can say, yeah, I've got a practice that's a bit like that. Let's just see why it works there and whether I could use it. But it's about granularity, not picking the thing up lock, stock and barrel and saying, we'll do one like that.
I think sort of things I was talking about or looking at, I mean, some companies are still not fully, like I think a lot of auto companies, they're focusing heavily on machine learning because they want to do autonomous vehicles, but they're not doing that, they're not actually doing much of it on their manufacturing, right? So it's just like, they're actually not seeing, so some of just the kind of going around, you could sort of see people, oh, that's what they're doing, like eye-opening, because some industries, it's like they haven't done that stuff. It's been separate. Pharmaceuticals is another one I spend a lot of my time in. You know, they are not, digital stuff for them is like very new. So just getting out to anybody, and now one of the problems is in the space, the leaders that this world, machine learning, they're extraordinarily secretive. Amazon is a leader. It's the only company I've ever visited where, you know, you typically get escorted to companies. They would escort me to the bathroom. That's how secretive they are. I've never been more, you know, talking to the bathroom. They are really, they're incredibly secretive, and so they are not allowing it. Google does not allow. They'll let people come to their you know, they'll take some tours, but the Japanese companies were incredibly open, but we're not seeing that. Facebook, Microsoft, they are unbelievably secretive places, paranoid, secret, frightening.
Okay. So maybe keeping our borders for the moment narrowly within the idea of the digitalisation of manufacturing, are there any ideas from the floor about who we should go and look at, or how can we let Mike? Oh.
I think you were asking about questions.
Okay, well I'll come to you immediately for the next question, but I was just going to think about the process of learning and copying and seeking out, and if anyone had any observations on that. Yes. Yeah.
I was going to suggest that, I mean, you mentioned Facebook, Google being very secretive, but also, and you talk about organizational learning, but there's possibly also space for looking at inter-organizational learning, because Facebook and Google, while they're very secret, they also produce enormous amounts of open source software, and a lot of their underlying processes, including, you know, cooling of plants and building more efficient data banks and things like that. Those are actually out there, and anybody could take the software and, you know, if they had enough resources, build stuff with it. So in some ways, it would be interesting to look what sorts of things are happening there, because there's social elements to it as well as the technical ones. You know, how the knowledge is passed around, how it's learned, how it's communicated, and, you know, what are some of the business processes and business thinking around sharing it and building on the learning from across competitors.
Okay. Thank you. Yes.
Hi. I work as a finance director for engineering companies and technology companies. So if we assume that machine learning is eventually going to be superior to organizational learning, if we assume that, if advances continue and IT and it just gets overwhelmingly better to do machine learning, then there's got to be some point for businesses where they have to invest in machine learning. Otherwise, someone else is going to have their company. To Mike's point, yeah, with his old black and white photo. So if we see these trends continuing if we look at these mature industries, and it's really interesting to hear that you've got these frontier new technologies, self-driving cars. Of course, you're going to do machine learning in there. You couldn't do it any other way. But it's that, for me, it's that inflection point of when does that new machine learning kick into the mature technologies that's going to be really interesting.
So we've got a question on where's the inflection point. Mike, do you want to give us your question? I'll pick up another question as well, and then we'll give the panel a chance to think about them. So
you're telling me what my question should be again? No. Sorry. Okay. Okay, sorry. So I want to not lose something about Dave, I guess, which was he inspired me enormously as a classroom teacher. The first time I'd seen a class debrief for the energy and enthusiasm that he brought. But what he did nearly always, not always, was manage to tread a fine line between being an enthusiast for new technology, machine learning, ML, now is very much mot de jour, 3D printing, additive printing. I'm being a salesperson for that technology. And so I was sort of intrigued really to put back to the colleagues, in the classroom, how do we present new technology in a way that isn't just, oh, and you should buy shares in this, but is giving students the tools to understand whether it's genuinely new and not just shiny.
Thank you very much. Let's take one more question. Yeah, from Paul.
Great, thank you. I can't quite remember if it was you, Matthias, or whether it was Mike, who referred to Dave as an industrial systems architect. So just to explore that a little bit more, and maybe Gary, you publish a bit with David Teese on the kind of the notion of the ecosystem captain. Sort of, you know, look at it in a very big scale way, and again, something that Dave championed a bit. Be just interested in more, just unpack that a bit more.
Thank you. So we've got 3 questions. First one is about when will we know we've hit the inflection point, or when is that coming? How do we present the technologies in class? And to comment on this idea of the ecosystems and the value architectures. So I don't know, who would like to go first?
Just quickly, I mean, I think the inflection points are impossible to predict in advance. They're always in retrospect obvious. It's like evolution. Evolution is obvious in retrospect, but actually it's not forward, but backward is. And so that's one of the dangers. And it ties to actually the second point around how do you present these to your students and get them excited. And then kind of back to your problem as a finance director. It's part of getting, I actually use a lot of historical examples. So if you look at, there's a famous entrepreneur, technologist, started several important companies, was talking about the future of the electric car, that within a few years all cars would be electric. So I was asked my students, who is that? They'll say Elon Musk, of course. He said in 3 years, you know, all cars will be electric. What was it? It was Thomas Edison in 1911. And Ford Motor was investing more in electric vehicles on inflation-adjusted terms in 1911 than they were today. What they couldn't predict was the invention of the electric starter changed. The reason people hated early cars were dangerous. They could take your arm off. So what happens, the trajectories of technology they're complex interactions of variables that come together that create inflection points. So for you as a finance director, so that actually should teach the students about some degree of sobriety around technologies. Although most people then accuse finance directors of being too sober about new technologies, because the lesson there's got to be a little bit of pre-investment of learning, small experiments, so that you can't predict when the inflection point comes, but when it comes, you have to be ready to pounce, because then things move quickly. So you have to be sober, but you've got to be doing some sober experiments to be ready. So. And I think that's the only healthy balance we could really tell you. In retrospect, it'll be obvious whether you were way too early or way too late. And I think it kind of ties back to the broader point around these technologies occur and happen involved within very broad industrial architectures, and which actually just amplifies the degree of it's the complexity that leads to the ambiguity around their evolution. Its technology predictions are very, very hard to do, and I tried not to do them. I didn't do them here. I just said this is what we know today.
Well, I think we've been inflexed a bit, if you see what I mean. Some inflection point has already passed. Judging by the rubbish that comes on my screen just because I bought a barbecue through Amazon, and so on. So there are things going on which I think we can't see, and I actually think it's extremely dangerous. Whether you invest in it or not is your problem, but I think in terms of an inflection point, I think we're much faster up the curve to things we don't understand than we like to admit. I think to the point about teaching, giving people an understanding of how to be objective about assessing a technology, I don't think we're very good at that. Probably I haven't read enough. But I don't think we are good at it because we're not very good at unpacking the nature of a technology and what systems it influences and the degree, what degree that influence might be. So I think there's the researchers in the room, I think that's still a huge open question. There's a real danger that we get excited by the whiz-bang, and just for a bit of fun, and I, as usual, was completely wrong. I was chairing a group talking about additive processing, and I introduced today by saying, well, I think if you want a process that's slow, inaccurate, and expensive, this is the one for you. So they love me. But more seriously, I'm not sure we understand how to do the kind of educating that you're talking about, Mike, as if you didn't know that. To the ecosystem and architecture point, I suppose I use the word industrial system architect really to try and capture something that we don't do very well. That is, we teach great engineers, we teach great managers, of course. We even teach some strategy, I suppose. I suppose I separate into technology and operations and strategy. But at the top of that heap have to be people who know those things, don't just know them, know how to stick them together. And analogies are always dangerous. But what architects have to do is say, what's this building for? Who's going to use it? How do we choose between metal and concrete and bamboo? And so those kind of questions, the ability to answer those kind of questions for an industrial system seems to me something that we ought to have more people capable of. I think that's a rather unnecessarily long sentence, but you see what I mean.
Thank you. Matthias.
Well, maybe just to add to Mike's point, I think it's a real challenge. It's very easy to fall into the trap of just reading the Wired, MIT Technology Review and The Economist and just cobble together a lecture on how any technology will change the world. And we must become honest brokers. And I agree with you, we are not very good at that. But I think the second thing is, the first thing is we probably will have to go out and see the technology in action. So it comes back to what Dave would tell us, how and why to do a factory tour. That applies to new technologies, right? Go get your hands dirty, put your hands into the powder, see what it's like, fish out parts for yourself, see how long it takes. How long does it take for a machine to cool down? What goes wrong when it goes wrong badly, just to see it firsthand. And secondly, I think we may well eventually have to say goodbye to a few things that we like to teach, and that comes to your point, right? We probably will have to also hold up the mirror to ourselves and say, is that still relevant? Do people still need to know about the EOQ or not? And the answer is probably no.
If I might add in a thought that's been troubling me for a while on this theme, and particularly picking up Paul's point about the architecture and the ecology of these things, is that we are in business schools predisposed to teach and assume and even research on the assumption that technology is something that goes on within companies as opposed to something that goes on within communities of companies. And it's very difficult to tell stories and have a narrative about complicated new technology development without having an Elon Musk in the story or having a heroic organization. But in fact, if you look, I think, in quite a lot of developments, certainly in the auto industry, what you see is technologies, the locus of technology development is not in one particular organisation. It's spread out amongst a diffuse network of highly linked organisations. And the trouble is, journalism doesn't work like that. That's too opaque a story to tell. So we end up retreating back into a sort of a more simplistic narrative. Let's take a few more questions. I'll do the same again and harvest 3 to give the panel time to think. Yeah, Mark.
Well, first of all, thanks a lot for really, really interesting presentation. So I'm from the same tribe as Matthias. I'm German, which means I don't have a sense of humor and I love manufacturing. And going a bit leveraging off on Steve's comment about larger communities, we're looking at 3D printing, at machine learning, at AI, and we're trying to make manufacturing in Western countries more competitive. Are we looking at the right thing? Or putting it another way, if manufacturing in the United Kingdom had the same institutional support, tax breaks, bailouts, the rest of it that financial services had, would we all be driving Morris Motors cars? And so when we look at, and going back to Mike's talk, and then Gary, you've written a lot about bringing manufacturing back into the US. Is it really about pushing the technological frontier about 3D printing, AI, or is it just simply stuff like taxes, like education systems, or giving simply the same type of preferential institutional support to manufacturing that financial services tends to enjoy in many Western economies?
Thank you. Janet.
Hi, this is a question for Gary, really. I was interested in the difference between machine learning and organizational learning, because today I was talking to somebody who, to carry on your interest in airports, he's doing a project with a large international airport where they've done a lot of work already on rehearsing and acting, role-playing different emergencies that the airport might have. And so they're trying to go beyond that now to capture that, not as a machine learning kind of opportunity, but using artificial intelligence. And I wondered, given what others of you were saying about IT pouring concrete on the flexibility of an organization, do you think that examples of companies trying to capture their expertise in artificial their occasional events, not day-to-day events in artificial intelligence systems is a bad idea or a good idea?
Okay. Thank you very much. And Hiram.
So I kind of want a little bit on Mark's question and also Steve, your point of view, like sort of your comment about Dave as a citizen of everywhere. But if you start to think through these technologies, so Gary, if you think about the codification, so we know machine learning really is only good at one thing, right? Pattern recognition, right? And many people say that now that with backward propagation, it's sort of almost at the end of its cycle, not at the beginning of its cycle, right? If you think that it can do that for a lot of things that can be codified, just like specific purpose equipment, and so the organizational learning fits in those gaps in between that kind of stuff. And you think through kind of where we're talking about locating manufacturing or even 3D manufacturing, can you raise the implications of this kind of architecture to the discussion we have about inequality, and particularly about kind of what I want to call the differential activities that take place in different places? So if we have not only just an income inequality, but geographical inequality, and if manufacturing, at least in the Trumpian world, was to kind of bring back some of those income opportunities to other workers, do any of these things that we've talked about here help solve that problem or help exacerbate that problem?
Very, very good. Thank you. So, panel.
I'll start, I guess, because I can tie a couple of the points together. So first of all, I do think one can use the various, I'll call these advanced computational technologies, so beyond just machine learning to sort of AI. It certainly can be used in concert. It sounds like what they're doing there is really fascinating, because you could use the computer to generate scenarios that maybe you would not have thought about. There's some scary things that you could use a computer to generate terrorist scenarios. And by the way, if you could do this, the security forces could do it to generate their scenarios. So can the bad people, right? So one thing we know, at least I'm coming to understand, or I've been taught, is one thing that these things can do is generate lots of variety. So it's, even in design, you now have algorithms to generate designs, but selecting or picking among them is still fairly human, right? Sort of what's going to be well. There's a lot more intuition there. I think these technologies, though, start to potentially, look, they do, so I've never thought advanced manufacturing was sort of the answer to a competitiveness problem in a country, particularly where there's things like robots can be bought. So, I hear people say, oh, you get this debate in the U.S., if we could only just put robots in, we'd have great manufacturing. I say, well, if you can buy the robots, so can anybody else. In fact, actually, China's the largest buyer of robots these days. So, I do think do these technologies contribute to inequality? That is a huge, I don't know. So I'm just going to say, I don't know. That's been widely debated. I think what they tend to do, all technological change, creates winners and losers. On average, the winners win bigger, so societies are better off, but that's cold comfort if you were among the losers. And so you tend to get that. I mean, some of the better work on inequality these days is showing that wage inequality is generated by lack of competition, because then you get more productivity. If low productivity firms can survive in your economy, then they become a source for hiring low-paid labor, right? So unproductive firms can only survive if there's low-paid labor. So there's some newer thinking around that whole issue, which is probably separate from the from the technology. I would agree with the point that we have had policies. I've often been, Dave and I wrote I think it was an op-ed in the Financial Times about this some years ago, about the role of manufacturing. It's actually, people always talked about, we don't want to have an industrial policy or manufacturing and support it. That's not, that's not very capitalistic. We need free markets, et cetera. But we put out that all the ways in which governments, particularly the U.S., I don't know the policies as well here, but the U.S. government, we do lots of things to subsidize services. So mortgage interest deductibility is a huge, I mean, you can only get your mortgage from domestic banks. So it actually provides a huge boost to the banking industry. There's lots of things we do that subsidize services or reduce taxation on carried interest for private equity. It's just, imagine if you got to pay your top tax rate for a worker in manufacturing was 15%. You'd have a lot more workers in manufacturing. So we've distorted it. So you're right. I mean, some of the rebalancing, some of kind of industrial policy for manufacturing could be called let's just level it out and then see what happens. I think there is some truth. I think there is some of that. And some of it, though, I do agree is the way it's been managed, and so it's not just purely a policy, whether it's 50-50 or 70-20. I can't tell you exactly, but I'm a strong believer the management, the way it's been managed, has often contributed to the downfall. But the policies sure haven't helped and have often hurt.
Matthias, Mark, if I can ask you for your brief closing comments, because we'll have to move on to the next stage of the evening.
Janet's question's too hard, so I'll dodge that one. I think the other two I shall use. I've only got one tool, which is the hammer of the industrial systems architect, so I'm going to use that to bash both questions. But a tad more seriously, clearly those economic levers you can push and pull, and the social implications for people are all connected. You can't consider them all in separate buckets. And we've tried over the years to try and educate a generation of people who know a little bit about all these things, but they have to stick it together themselves because we're not very good at understanding the nature of those systems and their dynamics. So I think that's my answer to the other two.
I would consider the question bashed.
Thank you very much. Thank you to all our speakers who've done a brilliant job this evening, and thank you all for coming. I think we've done Dave proud and a brilliant evening of discussion, and there's still work to be done. And thank you all. Thank you very much.